Hi there, and welcome back to Lean Reads, the channel where we share powerful insights and personal growth lessons through great books. Have you ever wondered where we truly come from? Not just as humans, but as part of the universe itself. In Origin Story, David Christian connects the dots from the Big Bang to modern society. Stick around, because this book might just change how you see the world and your place in it. If you enjoy what you hear and want to dive deeper, we've included a link to the book in the description below. Now, let's get started. Origin Story 2018 invites us on a sweeping journey through the story of the universe, from the birth of the cosmos to the present day. The book offers a clearer view of the key factors that shaped the extraordinary diversity of life, from the emergence of single-celled organisms to the development of agriculture. It is rightly described as an epic history of humanity's origins. David Christian is a professor of history at Macquarie University, Australia, and co-founder of the Big History Institute. Together with Bill Gates, he also co-founded the Big History Project, which provides valuable resources to schools for teaching the history of the universe. His 2011 TED Talk, The History of Our World in 18 Minutes, has been viewed more than 8 million times. Explore the grand epic of the universe and humanity's role within it. Throughout history, human beings have sought to understand the world and their place in it. Across different eras, races, and religions, people have created origin stories to explain the beginnings of humanity. Animals, the earth, the stars, and the cosmos. Globalization and today's dynamic knowledge economy have eroded our reliance on traditional myths about human origins. Yet even with all our modern science, we still do not fully understand the conditions that produced our existence. Origin Story presents us with the greatest narrative of all: how from nothing the universe, stars, and planets emerged, how the right conditions came together to create life, how living beings learned to harness energy from the sun to leap forward in complexity, and how millions of years later humans harnessed energy from agriculture and fossil fuels to create their own great leap. The Big Bang. 13.8 billion years ago, the Big Bang marks the beginning of the universe, one of the most pivotal events in human history. The origin of humanity is thought to have unfolded through what scientists call Goldilocks moments, periods when conditions were just right, not too hot, not too cold for complexity to emerge. But what about the Big Bang itself? The truth is, we don't really know what conditions allowed our universe to come into being. Perhaps the words of science fiction writer Terry Pratchett explain it best. In the beginning, there was nothing, which exploded. At the moment of the Big Bang, the universe was smaller than an atom. To put this in perspective, the human mind struggles to comprehend the scale of atoms. But imagine that you could fit 1,000,000 atoms inside the dot of the letter I. In the very beginning, there was only energy. Within fractions of a second, energy differentiated into distinct forces: gravity, electromagnetism, and others. Almost immediately, simple matter formed, which then combined into more complex structures. Protons and neutrons, tiny subatomic particles bound together to form nuclei. All this happened within mere minutes. As the universe cooled, the process slowed. Roughly 380,000 years later, electrons were pulled into orbit around protons by electromagnetic force, forming the very first atoms: hydrogen and helium. The universe began as something unimaginably small. Every particle of energy and matter we see today has been expanding and evolving from that first instant. The birth and death of stars. 12 billion years ago, when we look at the night sky, it's easy to believe that stars will last forever. But in fact, stars did not appear until about 100 million years after the Big Bang. At that point, gravity and matter combined to form what we now call Goldilocks zones, conditions just right for stars to ignite. In the earliest universe, everything resembled a mist made of the tiniest particles. In certain regions, where matter was denser, these clouds grew thicker. Gravity pulled atoms together, increasing both collision and heat. Over time, these dense clouds grew hotter and more compact. When the core of such a cloud reached 10 million degrees, trillions of protons began fusing into helium nuclei. This process released a staggering amount of energy comparable to the explosion of a hydrogen bomb. The fusion stabilized the core into a self-sustaining structure, a star, destined to burn for millions or even billions of years. Today we see stars gathered in great cosmic cities, galaxies. Our own Milky Way alone contains hundreds of billions of stars. Yet the death of stars has been just as important for the universe and for humanity as their birth. When a massive star dies, gravity crushes it and triggers a colossal explosion. For an instant, the energy released rivals that of an entire galaxy. In those fleeting moments, most of the elements on the periodic table are forged and flung out into space. These stellar deaths enriched the universe, formed the raw material of our Earth, and ultimately enabled the rise of human life. The birth of Earth and the solar system. 4.5 billion years ago, Earth formed about 4.5 billion years ago from the accumulation of debris left behind by the formation of our sun. The sun has given us light, warmth, and the energy needed for life, but it also shaped Earth itself. After the sun's birth, clouds of gas, dust, and ice orbited around it. The violent explosions within the sun expelled lighter elements like hydrogen and helium, while heavier elements such as oxygen, aluminum, and iron condensed in closer orbits. This explains why the inner planets Earth, Venus, and Mars are rocky, while the outer planets contain more gas and ice. Over millions of years, dust and particles collided, sticking together and forming larger bodies. Some grew massive enough for gravity to pull in even more material, evolving into asteroids, moons, and eventually planets. The evidence of this chaotic process remains visible today. Uranus' unusual tilt and its rings are likely the result of a catastrophic collision with another large object. Similarly, our moon may have formed from a collision between Earth and a Mars-sized planet, the debris eventually merging into a single celestial body. For a long time, humanity knew only of our solar system, the sun, its planets, moons, and countless fragments orbiting around it. But in the last 30 years, astronomers have discovered that most stars host their own planets. This means there could be billions of planetary systems across the universe. Scientists are now studying the conditions that might allow life to emerge on other worlds. What is life? At its most basic, life is made of billions of tiny molecules working together inside protected cells. Life can absorb energy, adapt to its surroundings, reproduce, and evolve. Under the right conditions, the molecules that make up life can arise spontaneously. In 1953, Stanley Miller, a chemist at the University of Chicago, conducted a famous experiment. He placed hydrogen, methane, water, and ammonia into a sealed system. By heating and electrifying the mixture, he created amino acids within a few days, the organic building blocks of proteins. This experiment demonstrated that, given the right conditions, the fundamental ingredients of life could form naturally. Earth had precisely those conditions: a delicate balance of temperature and chemistry. The role of temperature and carbon temperature is critical for both the origin and the maintenance of life. Earth possesses systems that regulate its temperature in a self-stabilizing cycle. When rain falls, it carries carbon into Earth's crust, where it can remain for millions of years. Volcanoes then release some of this stored carbon back into the atmosphere. Lower levels of carbon mean less carbon dioxide and cooler temperatures. If Earth becomes too cold, rainfall decreases, less carbon is stored, and carbon dioxide builds up in the atmosphere, warming the planet. If Earth becomes too warm, rainfall increases, more carbon is stored, and global temperatures fall again. This remarkable feedback loop has kept Earth's climate relatively stable, even as the sun has grown hotter over the past 4 billion years. Other planets such as Venus did not have this balance. Venus's atmosphere is overloaded with carbon dioxide, making its surface hot enough to melt lead. The first life forms, given these favorable conditions, primitive life emerged. The earliest life forms were prokaryote single-celled organisms that lived in chemically rich volcanic vents on the ocean floor. Though unimaginably small, hundreds of thousands could fit inside a comma on this page. Prokaryotes could still respond to changes in temperature. Their survival set the stage for evolution. But how did these simple life forms evolve into more complex organisms? Photosynthesis and the oxygen revolution. The answer was photosynthesis, the process of converting sunlight into biological energy. This breakthrough made energy virtually limitless, allowing prokaryotes to spread across the planet. About 3 billion years ago, a new form of photosynthesis emerged that produced oxygen as a byproduct. By 2.5 billion years ago, oxygen levels in the atmosphere had risen dramatically. Oxygen atoms combined to form the ozone layer, shielding Earth from harmful solar radiation and allowing algae to thrive at the surface. For the first time, Earth's environment became cleaner and safer for life. But for many prokaryotes, oxygen was toxic. The so-called Great Oxygenation Event wiped out countless organisms, forcing survivors into the deepest parts of the oceans. Meanwhile, the sudden rise of oxygen triggered global cooling, and Earth entered a 100-million-year ice age. It may seem disastrous, but in reality, Earth's self-regulating systems kept conditions within habitable limits. The rise of eukaryotes and sexual reproduction. During this period, a new kind of organism emerged. Eukaryotes. Unlike earlier cells, eukaryotes could extract oxygen from the air and use it efficiently for energy. This helped stabilize the atmosphere and encouraged the spread of life. Eukaryotes also introduced something revolutionary: sexual reproduction. Instead of simply cloning themselves, they combined genetic material with a partner. This ensured variation, even the smallest changes, in every new generation. More variation meant more possibilities for evolution. From this point onward, life began to expand dramatically, setting the stage for the incredible biodiversity we see today. Evolution, extinction, and the rise of humanity. The evolution and eventual extinction of the dinosaurs opened the path for large, complex organisms to thrive, ultimately paving the way for humans, with favorable conditions. Plus the energy boost from photosynthesis and the ability to process oxygen, single-celled organisms evolved into multicellular life. plants, fungi, and eventually animals developed and migrated from the oceans onto land. Photosynthetic plants consumed vast amounts of carbon dioxide and released oxygen, creating the oxygen-rich atmosphere we breathe today. Life adapts to land. The move to land changed evolution in profound ways. In water, gravity was not much of a concern. On land, however, plants needed structural systems to resist gravity, enabling them to stand upright. They developed vascular systems to move fluids internally. Animals, to adapted, they evolved circulatory systems like our own hearts to transport nutrients throughout their bodies. Intelligence as an evolutionary advantage. Natural selection also favored the processing of information, because information is key to survival. Being able to recognize threats, distinguish safe plants from poisonous ones, or detect opportunity meant life forms that could think better had an edge. The fall of the dinosaurs, but evolution was not the only driver. Extinction events also reshaped life's path. 66 million years ago, a massive asteroid struck the peninsula in what is now Mexico. Dust clouds blocked sunlight, creating a long winter and acid rain. Half of Earth's plant and animal species perished. Large creatures like dinosaurs were especially vulnerable. They required far more energy, which became scarce in those conditions. For mammals, however, this disaster was an opportunity. Small, rodent-like mammals required less energy to survive. With the dinosaurs gone, they flourished, eventually diversifying into many forms. Among them were the primates, the ancestors of humans. The evolution of humans by cosmic standards. Humanity is still very young. The universe is 13.8 billion years old. The first complex life appeared 600 million years ago. Humans branched off from other primates only about 6 million years ago. The first major difference was bipedalism, walking on two legs. This required narrower hips and skeletal adaptations, setting humans apart from other primates. 2 million years ago, Homo erectus learned to use tools and control fire. Cooking food reduced digestion time, allowing human intestines to shrink. With smaller guts, more energy could be devoted to the brain, a critical leap forward. But the truly revolutionary changes came with Homo sapiens, appearing only a few 100,000 years ago. What made them unique? The power of language. The answer lies in language. While many animals can communicate, their systems are limited. Chimpanzees may use a few hundred words, but they cannot convey complex information. For example, there's a lion 5 miles south. Humans, however, developed language that was both precise and infinitely adaptable. This was a game changer. Language allowed humans to accumulate, preserve, and transmit knowledge across individuals and generations. It meant that discoveries and skills did not die with the discoverer, but could be built upon. This exponential sharing of knowledge enabled humans to use resources more efficiently and innovate in culture, technology, and survival. Population and expansion. The results were extraordinary. About 30,000 years ago, Earth was home to only 500,000 humans. By 10,000 years ago, the population had risen to 5 to 6 million, a 12-fold increase. Energy consumption rose 12-fold as well. At this point, humans had spread across the globe from Siberia to Australia. These small communities had diverse diets, better health, and rich cultures. They told stories, danced, relaxed, and painted on cave walls. The agricultural revolution, a transformative leap for humanity throughout history. Certain innovations such as photosynthesis have radically transformed the trajectory of life. For humans, the next great breakthrough was agriculture, developed in response to growing population pressures. The Natufians, a community along the eastern Mediterranean coast, originally numbered only a few hundred people. As their numbers grew, they could no longer rely on foraging or the shrinking amount of land available. Instead, they turned to new techniques to increase the productivity of the soil they already had. At first, farming was backbreaking work. The skeletons of Natufian women show grinding wear, likely from hours spent milling grain each day. Yet necessity forced persistence, and over time agriculture began to reshape human life. It marked a giant leap in humanity's ability to master energy and resources. For example, while a single farmer might generate only 75 watts of energy through their labor, a horse could produce 10 times that amount. This allowed deeper plowing and greater hauling capacity, dramatically increasing efficiency. From villages to organized societies, as populations continued to grow, human life underwent profound change. Villages became common, and with them arose the need for new rules, norms, and cooperation. In Mesopotamia, modern-day Iraq, rainfall was scarce, but two mighty rivers, the Tigris and Euphrates, provided water. Early farmers dug small irrigation channels, but as communities expanded, they constructed vast and complex canal systems. These required thousands of laborers and unprecedented coordination, giving rise to organized leadership and the first ruling elites. Surplus and specialization improved farming techniques, eventually created surpluses, more food and goods than people needed for daily survival. This freed some members of society from constant agricultural labor, allowing them to pursue other crafts and roles. Archaeology provides clear evidence of this transition. The earliest pottery found in Mesopotamia was simple and individually made. But around 6,000 years ago, specialized workshops began mass-producing standardized bowls and plates, traded across wide regions. As surplus grew, so did specialization. About 5,000 years ago, in the Sumerian city of Uruk, records listed the first catalog of professions: kings and their courtiers, priests, tax collectors, silversmiths, and even trainers of wild animals, networks, roads, and trade. With surplus and rising populations, communities became larger, denser, and more interconnected. Rulers built infrastructure to expand trade and governance. One remarkable example was the Royal Road, built in the 5th century BCE by the Persian Empire, stretching 2,700 kilometers from Persia to the Mediterranean. It reduced travel time from 90 days on foot to just 7 days on horseback. Humanity was becoming increasingly accustomed to mobility, exchange, and commerce. People moved, traded, and shared knowledge and culture on a scale never before possible. The exchange of ideas in the fossil fuel revolution in 1492. Christopher Columbus became one of the first men to cross the Atlantic Ocean. Agriculture had taken nearly 10,000 years to spread across the planet. Yet within just a few centuries, humanity advanced at an astonishing pace as information and ideas traveled rapidly across oceans, exchanged faster than ever before. Isaac Newton's theory of gravity in the 17th century was made possible by the circulation of knowledge, for example, comparing how pendulums swung in Paris, the Americas, and Africa. For the first time, scientists could test their ideas globally. This acceleration of learning and innovation led to another momentous discovery: fossil fuels. Fossil fuels provided society with far more energy than agriculture ever could, and this unleashed a revolution in human life. Britain was the first nation to benefit. By the 1700s, they began using coal instead of wood. In the 1770s, engineer James Watt invented the steam engine, transforming industry and transportation. Steam engines even allowed miners to dig deeper into the earth. And between 1800 and 1900, coal production increased 55-fold. Coal changed the balance of global power. For example, Britain's steam-powered warships could overwhelm China's sailing fleets, securing control of Chinese ports in 1842. The discovery of electricity and the ability to convert coal into electric power sparked another wave of innovation, revolutionizing communication. Before the 19th century, the fastest way to deliver a message was by messenger on horseback. In 1837, the invention of the telegraph enabled communication at the speed of light. The Anthropocene, the age of humans. The Earth had entered a new era. The Anthropocene, the age of humans. For the first time in the history of the universe, one species had become the dominant force, reshaping the environment of an entire planet. Since World War II, humanity has experienced the greatest period of economic growth in history, fueled largely by fossil energy and technological innovation. Consider agriculture. The invention of synthetic nitrogen fertilizers dramatically boosted crop yields, enabling food production for billions. In 1950, when the author was a child, the world's population was 2.5 billion. In his lifetime, it has grown by an additional 5 billion. Economic growth has transformed human experience. Activities that defined life for centuries, tending crops, milking cows, gathering firewood, have all but disappeared for much of the population. Most of us now live in cities shaped far more by human design than by nature. The double-edged sword of progress. But alongside its benefits, the Anthropocene carries grave consequences. Economic growth has widened inequality. Even today, some 45 million people still live in conditions akin to slavery. Biodiversity is under unprecedented threat. Species are going extinct at rates hundreds of times faster than in millions of years past. Humanity has driven even our closest relatives, the primates, to the brink of extinction. Most alarming, we are destabilizing the very systems that keep Earth habitable. By emitting massive amounts of carbon dioxide, we are heating the planet. Current models predict that within the next 20 years, a warming world will flood coastal cities, disrupt agriculture, and unleash increasingly extreme weather. The future belongs to us. What will ultimately happen to Earth? In millions of years, our planet will be engulfed by the sun. Yet in the near term, the future remains firmly in our hands. The pace of change today is so rapid that the choices we make in the coming decades will shape both humanity and the Earth for thousands of years to come. For years, the Stockholm Resilience Center has modeled planetary boundaries, thresholds, which, if crossed, put our future at grave risk. Two of the most crucial boundaries are biodiversity and climate change. The bad news is that researchers believe we have already crossed the biodiversity boundary and are rapidly approaching the climate boundary. So what might a better future look like? In the 19th century, economist John Stuart Mill envisioned a future without endless growth. He imagined a world where the normal state of humanity is no longer a struggle for rising, a steady-state society in which no one desires to be richer. Could we create such a sustainable world, a world that reaches new levels of stability and complexity? Science now offers us a clear consensus on the impact of human activity on our planet. Agreements such as the Paris Climate Accord reflect this understanding. What remains lacking is determination. Many people remain skeptical of warnings. Few governments think beyond electoral cycles and short-term needs. And nearly all face pressure to prioritize national interest over global survival. Yet a sustainable world is a goal worth striving for. Humanity has the potential to endure not only for thousands but even hundreds of thousands of years, and who knows what astonishing transformations may follow. At its core, the story of human origins is a story of complexity. Over billions of years, complexity has emerged from a dark, cold, and seemingly empty universe. Stars, life, humans, and modern civilizations gradually arising from simplicity. In just a few centuries, the pace of change has accelerated beyond anything before, and today we live in a society so complex that it can alter the very future of Earth itself. The future, then, is not something to wait for, it is something we create. Reading Origin Story was nothing short of awe-inspiring. David Christian doesn't just give us a history book, he gives us a cosmic narrative, one that stretches from the Big Bang to the Anthropocene. It is humbling to see how the story of stars, molecules, and microbes ultimately connects to us. Sitting here in the present, trying to imagine our future, what impressed me most was the sense of scale. The book constantly zooms in and out from the unimaginably small atoms forming minutes after the Big Bang to the unimaginably vast galaxies teeming with billions of stars. And yet, somehow it always returns to the human story. How agriculture, fossil fuels, and language transformed us into a species capable of reshaping the planet. Another striking aspect is the idea of complexity. The universe, over billions of years, has produced ever more complex forms, from stardust to living cells, from organisms to societies, from myth to science. Seeing ourselves as part of this long arc of complexity is both inspiring and sobering. It reminds us that while we are special, we are also deeply fragile. The final chapters left me reflecting on responsibility. If humans are the first species to truly shape the fate of the planet, then our story is not just about survival but stewardship. We hold in our hands the power to either preserve Earth as a thriving home for future generations or to destabilize it beyond repair. Closing the book, I felt a mix of wonder and urgency. Wonder at the grandeur of our shared history, and urgency because the future truly belongs to us. Origin Story is not just about where we came from, it is about what kind of future we choose to create. This isn't just a history book, it's a roadmap for our future. If you want to dive deeper into the story of the universe and humanity's place in it, I highly recommend reading Origin Story by David Christian. You'll find the link below. And don't forget to like, subscribe, and join me for more journeys through books that expand the mind.